Okay, let's go ahead and work some word problems involving linear functions and quadratic functions. Here I'm going to just create a simple example here dealing with what we call linear depreciation. Okay, let's look at this example. A school buys a copy machine for $10,000. After 10 years, the copier will be worth $500 and need to be replaced. Assume that the value of the copier decreases by the same amount each year. This means linear depreciation. Answer the following. What is the value of the copier after t years? T between 0 and 10. You can't assume that this model would work outside that range that you've been given from 0 time when it's brand new to 10 years. Okay, so we're confining ourselves to value of t time in that range. Okay, and then I ask you specifically, what is the value of the copier after 10 years? Okay, all right. Now the first thing we're going to do here to work this problem is go ahead and define what the value is after t years. Okay, so let's say v, which is v is a function of what? Time t in years. This is the value of the copier in dollars after t years. All right. Well, it said the initial value of the copy machine was what? $10,000. So we'll say v of 0 is 10,000. That's one bit of information that we have. Okay. And then the second bit of information we have is v of 10 is $500. So it's estimated that its scrap value, so-called, its value when it needs to be replaced, in other words, is about $500. Okay. Now, what we're assuming here is a linear model, so that v is a linear function of time. Okay, so if you guys think about, my dependent variable is v, my independent variable is t. Okay, so v, which is written as v of t here for the moment, it should be what? Not mx plus b, but mt plus b. Okay, the independent variable is t instead of x in this particular example. Okay, now what we have in essence is the following. If I had points like this, say this is the TV plane, okay, what I've essentially been given are what? 2 points that lie on this curve, and since this curve is what? A line, that should be sufficient to completely determine the line and therefore the equation of the line. Okay, so what we really have is that t equals 0, rather, we've got what? It's worth $10,000. Okay, so v is 10,000 here. Okay, and now it's depreciating, right? So if I was to just draw sort of a graph, just a rough graph of this, you could see that what? It would have to have a slope which is negative. Yes, because the value is decreasing over time. So it's going to have a negative slope coming down like this. And after what? T is 10, we've got what? This point here, and it's supposed to be the value is $500. So I could think of it this way. I've noticed that I'm dropping for the moment the dollar signs here. We'll restore those later. Okay? After, when t is 10, the value is $500. I've really got what? When t is 0, the value is $10,000. I'll drop the comma on the 10 so we don't get this mixed up here. Okay? It'd be nice if we use semicolons there for points, but that's not our standard notation here. Now, what I'm going to do is come up here. Remember, I'm attempting to essentially find the equation of that line there. It's 2 parameters. What? The v-intercept and the what? M, right? The slope M. M is for slope. Okay? One thing I can do right here, you guys notice here, I already have the v-intercept right off. If t is equal to 0, and I substitute that in there, I've got $10,000 is v at 0, because that's the initial value. That's m times 0 plus b. M times 0 is what? 0 plus b is b. So b is actually $10,000. But you can see that graphically also that b is supposed to be, that would be the v-intercept is $10,000. So already I have part of the equation. V equals mt plus 10,000. Now we know that the slope is going to be negative, so that's going to be a negative number sitting in front of there. Let's go ahead and work that out. How do we find out what m is? Well, we've got to use this second point here. Okay? So let's see. $500 is v after 10 years, or v of t. So that would be what? M times 10. We would usually write 10m, right? Okay, we usually write the number before the unknown. M is unknown. Well, if you wanted to, you could write m times 10 there. Okay, if you want. Whatever. Okay, we got to solve for m. Okay, I'm going to do that by subtracting 10,000 on each side. So I'm going to go 500 minus 10,000. And then I'm going to do what? Divide by 10 on each side to isolate m. I think I'll do that right now. And you notice both these numbers are what? Up here are divisible by 10. So I'm going to use the distributive property. 500 divided by 10 is 50. 10,000 divided by 10 is only 1,000, right? So I've got my m. It's 50 minus 1,000. So that's the opposite of 1,000 minus 50. So that would be negative 950. Okay, so negative 950. By the way, you could interpret it this way. The value drops by $950 per year. So if you guys remember how the question was originally worded here, the copier decreases by the same amount each year. That number by which it drops each year is $950. Okay? All right, anyways, let's come back here. Now we're going to take that and we'll say v, which is a function of t. If you didn't write the t there, that'd be okay too. I'm just emphasizing. This is negative 950t plus 10,000. So there's the function, and this is in terms of dollars. There's the value of the copier as a function of time. Now again, I want to emphasize this is probably only good for this interval, a limited time. For example, if time was less than 0, it wouldn't be worth more than 10,000. Okay, and after if t is too large, it's not going to be worth a negative amount, necessarily. Okay, all right, everybody. Okay, so that's good. So we answered that part. This is essentially the answer to part A. To part B, what I'm really asking is the value after, what was it, 7 years? The value after 7 years shouldn't be really worth all that much after 7 years. So this is going to be the idea. I just substitute in t equals 7 in there, and I've actually got to perform a multiplication here. Let's see, 7 times 0 is 0. 7 times 5 is 35, so carry the 3 in my head. 7 times 9 is 63. With that carried 3, I've got 6650. Now that's negative, so what I'm doing is going 10,000 minus 6,650, and it looks like what? 3350. I'll put a dollar sign on the end there. That's the value after 7 years. Okay? All right. Now that we've got the question like this answered, let's go ahead and look at some problems involving quadratic functions. Okay, let's start talking about minimizing or maximizing a quadratic function by reviewing what we know about the vertex. Okay, we assumed before that we had what? y is a function of x given by what? ax squared plus bx plus c. Okay. One assumption we had here was the parameter a was not 0. Otherwise, you'd be just looking at best a linear function anyway. So we assume a is not 0. We found that the vertex had coordinates negative b over 2a, comma, f evaluated at negative b over 2a. We showed that by using completing the square here. We also mentioned that what? If you graph a quadratic function, it will be what we call a parabola. If a, the leading coefficient, the coefficient on x squared there, is negative, then it's going to be a frowning parabola. It'll be opening downwards like this. And the point we're calling the vertex will be a maximum point. So I've written it that way. On the other hand, when a is positive, it will be smiling, right? Positive people smile, negative people frown. Okay, if a is positive, it'll be opening upwards. And this point here will be a minimum. We still call that the vertex, okay? So it's contextual. Then we said it had some other things like there's going to be axis of symmetry through the vertex and stuff. But we don't really care about that in the problems we're about to work. But we need to remember this stuff. Okay? All right, now let's keep this in mind then. I'm going to give you a word problem here. Let's take a look at this. Okay, a ball is thrown up in the air so that its height above the ground after t seconds is, now I'm calling that a cap h of t. Cap h of t is negative 16 t squared plus 96t. Okay, this is not some phony situation. This is what would happen if you were to throw a ball upwards with an initial speed of 96 feet per second, upwards, directly upwards, okay? All right, neglecting air resistance and stuff like that. Anyway, here's the question. When is the ball on the ground? I.e., in other words, for which t is the height 0? Okay. Second question. When is the ball at its maximum height? So in other words, for which t? And what is the maximum height of the ball? Okay. Now you know this is what? This is actually a quadratic function of time here. Okay. Now, if I was to do this and have what? H as my vertical axis and t time is my horizontal, remember that's a cap h, then this function, since it's a quadratic, you can see is going to be what? Parabolic. Okay? This is going to be parabolic. Notice that at what? At t equals 0, I've got the height is 0. So the height actually starts at 0. It's shot upwards from the ground. Okay? Now, this is going to be what? A frowning parabola, because the leading coefficient is negative 16, right? That's negative, so it's going to be frowning. That means at some future time here, what's going to happen, it's going to hit the ground again. So the trajectory of the ball is not necessarily going to look like this because it's just going up and down, right? That's not what we're saying here, but we're saying the height above the ground could be modeled this way. Okay? The height above the ground could be modeled this way. And there's going to be, what, a high point up here. Okay? The vertex. Okay? Now, let's answer the first question first. It says, A, when is H equal to 0? Okay? Well, this is negative 16 t squared plus 96t is equal to 0. Okay, and you want to solve that. I would not resort to using the quadratic formula. It's too much work. This is much easier. You should notice that you can actually factor out a t from this thing. And then we use the zero product principle. The only way a product can be 0 is if it, what, at least one of the factors is 0. Let's take this factor t and set it to 0. Oh yeah, at time 0, the height is 0. Okay, we already knew that though. Or, here's another possibility for t. Negative 16t plus 96 is 0. Let's solve that. That would mean 96 is 16t, adding 16t on each side, dividing through 96 divided by 16. What is that? I think it's what, 6? This is also in seconds here. So 6 seconds. Also at t equals 0 seconds. I guess I don't have enough room to write it in there. So right here on my graph, I actually know the ball hits the ground again at 6 seconds. By the way, I cannot extend this idea downwards. You know, nobody's claiming it goes through the ground, okay, or anything. All right? All ready? You got it? All right. Now, there's going to be a high point up here, right? This is the vertex. Where do you think the t coordinate to that vertex is? Where do you think it is? What do you think it is? Okay? What do you think it is? It's going to be, you might guess already, it's right halfway between the two of these. Okay? I claim it's at 3. Okay? I claim it's at 3. It's right halfway between these, what we would call the t-intercepts. Let's go ahead and see that, though, using our formula here for the vertex that we created over here. Okay, remember that? Let's try it. Okay. All right. Let's see. So in part B, we've got, instead of y, it's h, but that's cool. Okay, and then instead of x, we have t, but we've got negative 16 t squared plus 96t. Okay, let's say the t coordinate of the vertex, we got negative b over 2a. Remember, b represents the coefficient on the first power of the independent variable. So that's on the t, over 2 times negative 16. And that's half of what I just got earlier, so that is indeed 3. Okay? So this is actually in seconds, right? Okay. This is going to be in seconds. So we've got 3 seconds. That's when it's going to reach its maximum height. Now, the very last part asks what the actual maximum height of the ball will be above the ground. All you have to do is actually calculate h at t equals 3. So let's put that in there. And this will be in feet. Okay? Alrighty? Okay. I would actually do this. Negative 16 times 3 plus 96 times the 3 on the outside, just for ease of calculation by hand. See, I factored out a 3 out of both of those. I know this is negative 48. From 96, that's 48, so it's 48 times 3. 3 times 8 is 24. And carry here. It's going to be 144 feet. So that's going to be the maximum height of the ball above the ground, and that will occur at 3 seconds. So if I come back here to my drawing, of course things aren't to scale here, but this would be 3, 144. Okay, that'd be the coordinates of the vertex, which is a maximum point on that curve. Okay, alrighty. Let me make one last quick point here. The ball was actually going up and down, right? This is not the actual trajectory of the ball. However, I do want to make a comment. If you are firing, a cannon or something, that's so long as it's not firing too far and you ignore air resistance, it actually does make a parabolic shape in the air. Okay, so if you throw a ball across the room, it'll may have a parabolic shape, more or less. Okay, all right. Okay, let's do another problem that ends up being a problem essentially finding the vertex of a quadratic function, or vertex of a parabola, if you wish. Okay, let's look at this little word problem here. A farmer has 400 feet of fencing and wants to create a rectangular pen for horses using the fencing. Okay, the pen will be bordering a river so that one side of the river will need no fencing. Okay? What should the dimensions of the pen be in order to do what? Maximize the area of the pen, right? So this farmer is interested in maximizing the area of the pen. Okay? That sounds like a reasonable thing to want to do. Now, in a situation like this, what I and most people like to do is go ahead and make a little drawing. Okay? Let's go ahead and just make a drawing of the situation. One little assumption I did not mention here that I might have included, I'm going to assume the river is more or less straight. So let's say that's the edge of the river here, the bank of the river. And then this person is going to create a rectangular pen. The horses assumably will not swim away. Okay, so the farmer does not need fencing on that side. Now, so here's fencing. Now this is rectangular so that the length of opposite sides are going to be equal. That's a little fact you need to know from geometry. Okay, this side here is where the river is, so although the length of this side is y, I don't really have to take that into account in what I'm about to do. Okay? Now, from this drawing, how much fencing have I actually used? I've used two x's and a y. Now, I'm going to be using all my fencing, so 2x plus y should be 400 feet, right? So I'll just throw that feet in here. All these measurements are going to be in terms of feet, or an area will be square feet, right? Okay. Now, speaking of area, what would the area of the pen be? The area of the pen would be, well, it's rectangular. The area of a rectangle is what? The base times the height, okay? So it's the product of the lengths of two adjacent sides. This would be x times y. Okay, now we're trying to maximize the area of the pen, so we're trying to maximize x times y. Now, how this differs from this problem differs from some previous ones is actually have what? Two unknowns. I've got the x and the y. So the first thing I'm actually going to do is write this problem in terms of a single variable here. Now, I think the easiest way to do that is come over here. And I've got this relationship between x and y. 2x plus y is 400. That would mean that I could isolate the y by subtracting 2x on each side of this identity above here. 2x plus y is 400. Okay? So that would mean y is always going to be 400 minus 2x. Now, bear in mind that x and y have to be non-negative numbers. Okay? All right. But that's obvious. I'm not going to bother putting that in right now. Okay, we have this relationship here. And then my area, maybe I'll call the area is A. The area equals A. That's x times y. So that's really x times 400 minus 2x. So A is actually a function of x. So I'll write that dependency this way, as we tend to do when we write functions. Okay, A is the dependent variable and x is the independent variable. And then when you multiply through, and I'm going to write the square term before the linear term here, and we've got negative 2x squared plus 400x. So what I'm trying to do is what? Maximize this, okay? Now, I do have that constraint that x better be greater than 0. I'll write greater than or equal to 0 there, okay? Also, y is going to be greater than or equal to 0, but I'm not going to write that right now. Okay? So, wait a minute. I'm dealing with what? A quadratic function again. Okay? So, if I was to imagine this thing, let's say I have a is the, what? The dependent variable, and x is the independent variable, then this thing is going to be graphically a parabola, right? Now, you can do this in your head. You can see if x is 0, the area is 0. That makes sense. If it has no width here, the area is going to be 0. Okay? And then this is going to be a frowning parabola again because the leading coefficient is -2, which is obviously negative. So this is going to be frowning. And you guys see, it's actually going to have another intercept over here besides 0. It's going to have another intercept, and we will have a vertex, a high point somewhere between 0 and whatever this other x-intercept is. Okay? Alrighty? Alright. Now, we could set this to 0 and solve, and then what? Take the midpoint of those two values, and that would be the x-coordinate of my vertex here. But this time, I think I'll go ahead and just use our formula for the vertex. Okay? I'll just say, what value of x yields that maximum area? Okay? I would want x to be -b over 2a, which would be negative, let's see, b in this situation is 400, and then I'm going over 2 times -2, and I actually get 100 for a, and I'll throw in the measurement there. So I should have 100 feet here. Okay, so I should have 100 feet here, 100 feet here. What's y going to be? Let's throw that in there. 2 times 100 plus y is 400, and you can see that would mean 200 plus y is 400, so that means y is 200 feet. Okay, so x should be 100 feet, y should be 200 feet. Okay, so if I come back here, this should be 100 feet, this should end up being 100 feet, this should be 200 feet. Okay, what's the area, the maximum area there? Maximum area would be 100 feet times 200 feet, which is 20,000, and then our units are square feet. Okay, so there we go.